In this section, we will provide an overview of the Matlab Simulink models developed for the rotary inverted pendulum hardware shown here. These Simulink models include the characterized plant dynamics in the multi-mode controller that provides both swing-up and inverted pendulum hold capabilities. We will then demonstrate the automated conversion of these Simulink models into SES Distributed Processing Plug-ins that can then be immediately used in either the non-real-time desktop environment or in the real-time hardware-in-the-loop environment. Okay, once the equations of motion have been derived, you can then input those equations of motion into Matlab Simulink. So I'm going to show you what we have for that. First, I'm going to bring up Simulink, and we'll open our model. As you can see, there are two colored subsystem boxes here. These are the pendulum controller and the pendulum plant dynamics, which are connected together to form a closed-loop system. The plant dynamics subsystem is feeding the angular position and rate data for both the swing arm and the pendulum to the controller. The controller subsystem then uses this information to compute the motor voltage that will drive the plant to the desired location. Now let's go ahead and look into the pendulum dynamics. This Matlab Simulink subsystem implements the differential equations that we derive for our plant. The motor voltage is the input to this system, and the outputs are the pendulum rate, the pendulum angle, the swing arm angle, and the swing arm rate. Both the pendulum acceleration and the swing arm acceleration are functions of the pendulum angle, the swing arm rate, the pendulum rate, the motor voltage in, and this denominator term over here. Now we're going to go ahead and look at the pendulum controller implementation. As you can see here, there are two controllers. There's a swing-up controller that drives the pendulum system when the pendulum is not in the upright configuration. And then there's a state controller here that's actually used for closed-loop control of the pendulum when it's near the vertical position. This S function over here is used to determine which mode the controller operates in. Now, if I open the state controller, you'll notice that there are four internal terms. These terms are calculated based on the error signals for the swing arm angle, the swing arm rate, the pendulum angle, and the pendulum rate. To calculate the gain terms that are in this state controller, I first linearized the nonlinear plant equations. Then I put those equations into state space form. I then utilized the linear quadratic regulator approach to sizing these gains, with an emphasis on controlling the pendulum position over that of controlling the swing arm position. Okay, let's go ahead and run this system. Before we can do that, we've got to go back to Matlab and set all of the coefficients that are utilized by these Simulink models. So let's do that. I have this M function here that'll handle that for us, so we're going to run that. Okay, as you can see, all the coefficients and gain terms have been computed and set. So let's go back to Simulink, and let's open up our scope here. Okay, let's check our initial conditions. We're going to set our initial rate for the pendulum to be 0. Okay, we'll save that, and let's go ahead and run the system now. As you can see here, we have the pendulum angle, the swing arm angle, the motor voltage, and the observed pendulum rate. Now here you can see the pendulum at the 0 position when the simulation starts. The 0 position is the down position. The controller detects this and it transitions into the swing up mode. It then gradually adds energy to the system by sending these motor pulses at the appropriate time. Once the pendulum gets close to pi radians, the controller transitions from the swing up mode to the hold mode and then rapidly stabilizes the pendulum at the vertical position. At this point, there is still an error in the swing arm position because the state space controller is configured with an emphasis on controlling the pendulum angle over the swing arm angle. However, the state space controller then slowly walks the swing arm into the 2 pi or 0 position while holding the pendulum upright. Okay, now that we're happy with the results that we've generated from the Simulink model, let's go ahead and convert this to a distributed process so we can use it in a real-time system with real hardware. The first step is to go back into Matlab, which I'm going to do here. We then run the SES-DP gen, and that'll bring up this dialog. We now need to browse for our model. So I'm going to click on the Browse button. I'm going to go to the model that we've just been working on. And that brings up this dialog here. As you can see, the tool has scanned our Simulink model and located all of the embedded subsystems within this model. The tool will convert the embedded model subsystems that we select into SES Distributed Process Plug-ins. We can then directly deploy these distributed process plugins into either the SES-DP non-real-time desktop environment or into the real-time hardware-in-the-loop environment. Before we can generate any code, we have to tell the system where to place that code. So we hit the Browse button, and we're going to put it in the standard location, which is the SES Distributed Process Plugins directory. We then need to tell it what prefix to assign the distributed process objects that this system's going to create. In this case, I'll just use SES INVPND. We then need to specify a frequency that the fixed step integrators are going to run at for each of the distributed process objects. In this case, we'll use 200 Hertz. And we select the two distributed process objects that we want the system to generate. So it's going to convert the Pendulum controller subsystem into a Pendulum controller distributed process, and the Pendulum dynamics subsystem into a Pendulum dynamics distributed process. To generate the code, we press the OK button. Now the system has completed the generation of the code for our distributed process objects. At this point, we can go into Microsoft Visual Studio and build the distributed process objects. The DP code generator automatically produces project files for various versions of Microsoft Visual Studio, as well as make files for Linux environments. So now what we need to do is add those project files to this solution. Then we'll add the Pendulum Dynamics project. And now we'll add the controller project. Okay, now the two distributed process objects that were just auto-generated by the toolbox are loaded, and we can go ahead and build these. And we'll build the debug version. And this version is going to run on the non-real-time environment, which is going to be on this machine that I'm using for the demonstration. We can then cross-compile for the hard real-time environments. Okay, now let's build the Pendulum Dynamics. And that's it. Now we have plugins that are ready to run for both the Pendulum controller process and the plant dynamics process. As you just observed, a simple mouse click has transformed our Matlab Simulink models into plugins that can now be loaded into the powerful SES distributed processing environment. And all of this was done seamlessly without touching a single line of C++ code.